I'd like to present to you Paul Kolano from NASA. He's going to be talking about stripe-aware tools for Lustre. Ladies and gentlemen, Paul Kolano.
All right, so as I'm sure all you know, Lustre has great performance, with the caveat being that if you know how to use it. So unfortunately, the tools that users are using to move files around and do things like that don't really know how to use it. So they don't take striping into consideration, so files end up on too few or too many stripes. There's really not enough parallelism to keep Lustre busy, so you really only achieve a fraction of what your available I/O bandwidth is. So the subject of this talk is really how to modify these standard tools to more appropriately support Lustre. So I'm going to talk about both stripe-aware tools as well as high-performance tools. Okay, so let's first talk about stripe-aware tools. Okay, so as I'm sure also you all know, stripe counts determine how many OSTs a file will be divided across. So this can significantly impact your I/O performance, well, either in a good way, so more OSTs gives you more bandwidth, or in a bad way, so more OSTs means more overhead. So striping is set when a file is first created and can't be modified without recopying the file. So I really want to specify your stripe count carefully at the beginning, or you may be sorry later. So how do you specify stripe counts? Well, the normal approach is to the default striping policy. So basically, any newly created file that hasn't explicitly had its striping set is going to go to the default. So the problem with this is, well, different file sizes behave better with different stripe counts. So a high default value, unfortunately, small files might waste space on OSTs, or they might generate more OST traffic than desirable for things like stat operations. And if you have a low default value, well, then large files suffer, so they have significantly reduced performance, and they result in imbalanced OST utilization. So you might have a multi-terabyte file sitting on one OST. So the second option is kind of just having the user manually stripe their files, so they can pre-stripe their files and directories with using LFS set stripe. Well, the problem with this is, well, lots of users may not even know what a stripe is. You have lots of scientists that are using these high-performance systems. They're not really file system experts. They may not remember to set the striping even if they know about it. And they really might not even know what an appropriate value is for their files and directories. And finally, their directories are going to contain mixtures of small and large files, just like the file system at large is. So really you have the same dilemma as the default case, whether to set to a low or high value. And so finally, kind of the option I'm going to talk about is having stripe-aware system tools. So these are kind of the approaches. You have these normal system tools that users use to manipulate files, just kind of automatically stripe files as they're moved around the system or whatever. So then you can kind of just keep the default low for more common small files, and larger files will just kind of magically get striped larger. So the problem with this is, well, few system tools really know about Lustre striping. So the solution to this is, that I'm going to talk about, is to enhance the commonly used tools with this knowledge. Just kind of taking a look at, well, what types of tools might we want this for? So if you look at a typical workflow in an HPC system, you might have the user remotely transferring in data to the file system, so using your standard tools like SCP or rsync or whatever. The user usually prepares the data for processing, so they might untar their files or uncompress them. Then they're gonna process that data on some compute resources. So at this point, we don't really know what they're going to use. There's all kinds of different things that they're using, but kind of the point of this is that we don't really care, because hopefully by that point the input files are already going to be striped appropriately by their manipulation through these other tools. Now the output, unfortunately, is still going to be based on the default or the user specified striping, since we don't really have control over that. And then after they process this data, they might want to prepare the results for remote transfer, so they might want to tar up their files again or compress them, and they're going to maybe remotely retrieve the files from their own system. And at this point, it's not really our problem, because we've striped it as well as we could, and then it's going to be on their system. So there's other activities as well. So admins might copy data between direct file systems to balance utilization using things like CP and rsync. Users also might copy data between their home directories and scratch systems or from backup directories or things using the same tools. And then they might retrieve their data locally from like an archive system, like again using the remote transfer tools. Okay, so how do you actually make these tools stripe aware? Well, it's actually quite easy. So since striping needs to be specified at file creation, basically you kind of look through the code and find instances of open when they're using the create flag. Then you want to determine, well, do you even care about striping at that point? So you determine if the target file is going to be on Lustre, so you can use some like StatFS for that and just look at the file type. Then you're going to determine the projected size of the target file. So this kind of depends on the application that you're looking at, how complex it's going to be. So things like CP, where you have a single source and single target, are pretty easy. If you look at something like a tar file creation, it's going to be a little more complex because you have to sum up the sizes of all the individual files that you're working with. Then you're going to compute the desired stripe count based on some kind of formula based on the size. So here you might also want to preserve source striping, so for something like CP or rsync. So you can use the Lustre API call to get the stripe count. So in our particular case, we look at if it's basically the stripe count is not the default, then we preserve it, otherwise we use our formula. Then finally, you're just going to switch out the open call with the Lustre API call to open the file with the stripe count that you want. So how do you kind of determine what stripe count you should use? Well, just as kind of a simple example, try to illustrate this. I did a 4-host parallel DD and then take a look at what the reads and write times are. So this is basically multiple processes on multiple hosts writing to different offsets of the same file. So here you can see in the write time, so you can see for large files, striping has a significant impact. It significantly increases performance. But you see at a certain point, there's really no further benefit from doing this. So you also see at this point at which you start getting no further benefit kind of is kind of moving left on the graph as the stripes get lower and the file sizes get lower. Okay, so the read case is a little different. So here, not only does, you do get a benefit at first from increasing the stripe size, but after a certain point, not only do you not get any benefit, you actually get a decrease in performance as you keep going. So it's not quite as clear as in the right case, but again, you kind of have kind of the best performance kind of drifts from so lower stripe sizes as you get lower file sizes. Okay, so these particular results kind of indicate maybe one stripe per 2 to 4 gigabytes might be best. This is just something to illustrate this, so probably needs further analysis. So basically we took these tools that users commonly use and this knowledge about striping and implemented a set of stripe-aware tools. So it's called retools, restriping tools for Lustre. So it's not really restriping in the sense of taking a file that exists and making it a file that has different stripes. It's more taking the value that it would have been striped at and instead striping it at a different value. Okay, so for kind of historical and possibly future purposes, all the tools have been named starting with M. You'll see why later. But the basic activities are kind of all covered in these basic user workflows and other activities. So whether it's archival and extraction via tar or compression and decompression, local and remote transfers, kind of all the steps in the user's typical workflows are covered by these tools. So the striping policy that we kind of did this before we even, at least I even looked at what the impact of different stripes for sizes are. So we kind of ignored the previous results and just set the formula for computing stripes at 1 stripe per gigabyte. So this is kind of based on just gut feeling by multiple members of the staff at NAS. Okay, so the main performance benefit of doing this is when the user runs their code on lots of different nodes in their computation, but there is some benefit just in the tools themselves. So we basically looked at just a single source file with 1 stripe. What were the performance or the time differences with the original tool versus having one that will restripe the file on or put it on a different number of stripes than the default. So for bzip, you get a pretty significant benefit during compression, but bzip definitely does not like having multiple stripes on decompression for some reason. So gzip, again, has very good results for zipping and almost no results for unzipping. You get some minimal benefit again for rsync, and finally for tar you get some small little benefit from just doing this on its own with nothing else. Okay, so stripe awareness is a good first step, because now we can kind of keep the default stripe count low for more commonly seen small files, so we can reduce OST contention and wasted space. And then large files are kind of going to be automatically use more stripes as they're manipulated just by the standard tools that users use all the time. So their computations on the files are going to have higher performance as they eventually go on the compute nodes and process it with thousands of nodes. And OST utilization is going to be kept in better balance. And finally, there's some modest performance gains just from adding this capability to the tools themselves. But these tools really, their performance still is nowhere close to what the raw Lustre I/O performance is. So now I'm going to talk about how you can make these tools high performance to take advantage of Lustre bandwidth. Okay, so the problem is most of these standard tools, they have no idea how to take advantage of the bandwidth. They weren't written for something of Lustre's performance. So the problem is they use single threads of execution that really can't keep the single system I/O bandwidth utilized. They rely on the buffer cache to do lots of things, which becomes a bottleneck. They're really written for simplicity, so they don't do things like overlapping reads and writes, and they usually only operate on one host. So there's all kinds of single system bottlenecks that are going to limit the max performance. And Lustre is really designed to work across lots and lots of hosts, so it's really not meant to really max out from a single host anyway. So the solution again is, we're going to try to enhance these commonly used tools with this knowledge so that they can take advantage of Lustre bandwidth. So this is actually a lot more complex than just adding stripe awareness. So you can add the stripe awareness in probably a couple hours, but making a tool high performance might take several months. So the things you want to do are kind of use multiple threads to keep a single host busy. You want to use direct I/O to just completely bypass the buffer cache. You want to overlap reads and writes with asynchronous I/O and use multiple hosts to get aggregate bandwidth. So basically, you want to kind of max out the parallelism that you're getting with the tool. And so once you start getting more parallelism, you have problems with large files. Now, if you start doing one file per thread or whatever, so you also want to kind of split the processing of large files into more parallelizable chunks. So the example I'm going to give for this is high performance CP. So I'll leave the rest as exercises for you. So MCP was kind of the original M util. So the M actually stands for multi-threaded and multi-node. So I just use those for the other tools, and maybe hopes of the future they might be parallelized with similar things. So the original behavior of CP is single-threaded. Basically, it's a depth-first search. The directories are created with write and search permissions. The file contents in that directory are then copied, and then eventually the permissions are restored to their original. Okay, so how do you parallelize this? So basically, use two different types of threads. So one, I have traversal thread, which is basically the original behavior of CP, except for in the case when it encounters a regular file. So instead of copying the file itself, it's instead going to push just a copy task onto a task queue. And then it's going to wait until the file is actually opened before then continuing and doing everything else that it used to do, like setting permissions and ACLs. And so the bulk of the work is done by these worker threads. They just sit there and pop these copy tasks from the task queue. Then they open the file and then push a notification so the traversal thread knows to continue. The idea here being is that once they've opened the file, the permissions and ACLs and everything don't matter anymore. Then they're just going to perform the copy, each thread doing its own copy. So now there's a multi-node capability as well. So this works just the same really, except for there's a manager node where the traversal thread is, and all these worker nodes, and just this a single thread for TCP or MCP handling. So basically, all the communication of the tasks between the traversal thread and all different worker nodes is handled just by these threads on each node. Okay, so how does this impact performance? So if you just multi-thread CP without doing anything else and worrying about things like the buffer cache, you get a very slight benefit, but as you keep increasing threads, you really get no additional performance. So you can do things like use fadvise to tell the OS that you don't really want you want the data again, and this does help. But really, to get true performance, the performance that you want, you just want the buffer cache to just get out of the way and use direct I/O. So you can see a significant benefit by using multiple threads in direct I/O. Okay, but we can do better because in a normal copy, basically the files are read into a buffer and then they're written out of the buffer, kind of in a loop. So we can actually use double buffering and asynchronous I/O and basically do reads and writes at the same time to try to kind of max out the parallelism that's available that's being employed on a single node. So here you see the benefits of doing this. So in the F-advised case, you don't really get too much of a benefit because, again, the OS is the bottleneck. So everything's going through the buffer cache, and this is limiting what you can get. When you go to the direct I/O case, you get quite a big benefit from doing this. And so basically, you're keeping the node as busy as possible. And okay, and so you can see here we're getting almost 10 times the performance of CP on a single node just by doing these additions. But we can still do better. So as I said, Lustre, as you know, is meant to go across multiple nodes. So we can actually add a multi-node capability to it and get even better performance by having multiple nodes work on the same problem. So here you can kind of barely see this poor little CP down at the bottom. That's the original performance. And as you keep adding more and more nodes, you keep getting better and better performance. So threads here don't have as big of an impact as they did on a single node, as probably the file system itself is so busy that just keeping it can't really keep up with all the threads on all the different nodes. So you still have a problem though, because if you just process one file per node, so in this case I was doing a transfer of 64 files, so each thread was kind of kept busy with one file. But if you have an imbalanced workload with like a single very large file, you still want to be able to have high performance. So you have to kind of break up the processing of it into smaller chunks, and then you distribute all the different chunks of the same file to different nodes and threads. So at least in my experience, Lustre doesn't really seem to like multiple threads in the same host working on the same file. And so you can kind of see that here where you get this flat curve, multiple threads on these nodes where it's really, there's no benefit. It's just, I don't know, for whatever reason, Lustre doesn't like that. So here you can see you're getting good performance even on the single very large file by splitting it up into different chunks. Okay, so the results now, CP performance with these modifications is now more in line with that of Lustre. So you're getting like 10 times the performance of regular CP on one node, or measured up to 27 times on 16 nodes. So based on an older file system, this is getting 72% of peak of the Lustre file system, assuming perfect overlap of reads and writes, like that the max is assuming perfect overlaps. So a side benefit of this is actually fast restriping. So this is restriping in the sense that the file already exists with striping, and you're going to move it to a new file with better striping. So basically, the only way to do this is to copy files. Well, luckily, MCP does fast copies and it's stripe aware. So you can just simply copy the file with MCP, and it's going to be fast, as well as restriping it to an appropriate value. Okay, so kind of in conclusion, modified standard system tools that are found by users to manipulate files in common workflows to better support Lustre. This is by both adding stripe awareness as well as high performance. So this is based on the original source code. So this is basically 100% drop-in compatible for the standard tools. So the idea is you simply replace the tools that already exist. So you don't really call it mtar or whatever, you just install it as tar. Now, I guess we don't quite yet follow this rule at NAS, this suggestion, but it's planned for the future. So by doing this, it's better for users because you're transparently achieving higher performance just by using the tools that they already use. And it's better for the file systems because it's reducing contention, wasted space, and imbalances in OSTs. So obviously you can make other tools in these standard workflows stripe aware, so things that weren't done like zip and SCP, things like that. And we can also make other tools high performance. So tar is a good candidate for this, and originally why I started with the mtar stuff is because it's widely used and it's extremely slow. And of course, we'd like a better analysis of the optimal stripe count formula. Okay, so finally, the stripeware tools, they're in the process of being open source. This has to go through all kinds of lawyers and stuff at NASA, so It takes a few months. If you're actually in the government, you can get it right now through a simple one-page form. It will eventually live at SourceForge when it's released. Now, MCP and a tool I didn't talk about, which is a high-performance replacement for MD5, some are available right now. So you can actually get them off of SourceForge. Here's my email if you have any questions or whatever, or I don't know if we have time now, but anyway, we can take questions now if you want.
I think we got time for a couple. Anybody? Andreas, we have a mic. Could you repeat his question?
Oh yeah, so I think the question was, is there any contact with the original authors of like the various tools like tar and CP and stuff? So no, I mean I haven't done anything. So.
Okay. Over here.
Do you allow the user to override the automatic stripe assignment? So the question was whether we allow the user to override the stripe assignment. Right now, no, there's no way to do that, but it will preserve striping. So if the user has optimally striped their file for their computation, so basically it's not the default value, it will preserve it instead of replacing it.
Okay. Thank you, Paul Kolano.